welcome to our second SPARC seminar series, and it is with pleasure that I introduce Professor Otto Gregory and Dr. Brian Berland to present this. Their bios in detail are on the link provided at the bottom of your invitation. Please go to that. I'd like to say that Otto has been working with Brian for the past year and a half, and they have jointly won a proposal from the Flex Tech Alliance, which is a good way to transition all the technologies that are developed under ALERT. And with that, I want to give the speakers as much time as possible. So go for it, guys.
Well, good morning, everyone. Just wanted to welcome you to this webinar. Today's webinar will focus on efforts to make a truly portable electronic trace detection system using our orthogonal sensors. When I say orthogonal sensors, we have a sensor system that can simultaneously interrogate a catalyst in two different ways. One is with a thermodynamic approach and one is with a conductometric approach. So BIPASS stands for an architecture to integrate everything into a very small sensor platform. And so what I'm going to go over today is the approach we use to miniaturize everything from the electronics, the sensors, the battery, the power supplies, everything to make this a truly portable sensor electronic trace detection system. And I wanted to mention also that our main focus has been explosives with the ALERT Center of Excellence. But more recently, we have branched out to detect fentanyl and other narcotics in the vapor phase, which is important to the Department of Homeland Security as well. And so I wanted to also acknowledge Brian Berland, my co-presenter, who headed up a large effort. And I don't know if you can see my cursor, but at the bottom here are all the partners in this large effort, which was almost a $3 million effort to do just that, to miniaturize our electronic trace detection system so that it could be integrated on a drone or a wearable device. And so that required a lot of effort to make that happen, because it's not just about the sensors, it's about all of the components necessary to make that. And this was funded by the Flex Tech Alliance, which you can see down here. To date, our portable electronic detection system was the size of a toolbox. So it really wasn't truly portable. And so all the efforts that we're talking about right now are going into making the system truly portable, okay? The media has coined the term digital dog nose for our thermodynamic and conductometric sensor. And so that's why this slide has that. Basically, our thermodynamic sensor is, if you can see my cursor, there's a substrate, a microheater, a dielectric layer, and a catalyst layer on one microheater. And on another microheater, it's all the same layers, and except for the catalyst layer. And these are actual photographs showing the actual size of our earlier sensors. The substrate here is aluminum oxide, which is about one millimeter thick, and the layers are, as you see here, and these measure about 8 millimeters by about 15 millimeters in size. We have tried to make a MEMS version of this, and that's what you see here. And for reasons I won't get into, that they were not very successful. So we originally started the program with two sensors, a catalyst-coated sensor and a reference sensor. And more recently, this is a rendition of what we've done more recently, which is an array of sensors, one reference with a whole series of catalyst-coated sensors with different catalysts, and then the flow control and pneumatics. And you can see this is pretty small. This is a quarter here. And the reason is that one of the applications for this effort is to put these sensors on drones. Imagine putting sensors on drones that could detect threats. You fly in without risking anybody, and you detect and then you fly out. The problem is that with some drones, some very stealthy drones, the payload, the maximum payload is 2 grams. So imagine having to have everything in the sensor system weighing 2 grams or not, which then including the power supply. And so that is the challenge here. So everything that I'm going to present today and Brian will present is in that direction. So basically our sensor works simply this way. There are 2 microheaters in a separate small tube, and they are coated with a dielectric, and that's what you see here. And the dielectric is used to isolate electrically the sensor elements from the catalyst, because sometimes the catalyst, depending on what it is, can be electrically conductive. And then after the dielectric, we put a catalyst on one microheater, and there's no catalyst on the other. And then we will hook those up to our data acquisition system. And then we will introduce the analyte. And we have mass flow controllers delivering equal quantities of the analyte-laden vapor stream. And then they pass over the catalyst-coated sensor and the reference sensor, and we subtract the difference in electrical power to maintain a constant temperature, and that is the heat effect associated with the catalytic decomposition of the molecule of interest. So this is a response of our sensor to 20 ppm TATP. You can see when the analyte is introduced, the response is almost instantaneous here. The response time is on the order of 3 seconds. And then there's a maximum in the response. And then when you remove the analyte, you see this decay. We would not be using this whole protocol in a real application. We would be using some kind of initial response and then essentially have a duty cycle to turn the sensors on and off, so we wouldn't have to wait so long to see if the analyte is present. So the idea to make this truly portable meant that we had to start at the sensor elements and reduce the thermal mass. So the aluminum oxide original sensor was 1 millimeter thick. And because of one of our partners, Energy, that you see down here, they were able to supply us with, starting with 40 micron thick, so 1,000 microns on the left, and then they supplied us with 40 micron thick YSC. And so the heating was much more local, the power requirements were substantially reduced, and the temperature of the catalyst was very specific because you didn't get a lot of thermal dumping into the substrate, spreading out the heat effect and having a distributed heat effect. Essentially, we were able to get a very specific response. And so the anisotropic behavior of the YSC material, its thinness or thickness, anisotropy as well, produced very different thermal images. So these are high resolution IR images of a microheater heated up to 175 degrees C, which is our typical operating temperature. And you can see that the YSC has much more localized heating. There's a catalyst actually sitting on top of this that's not obvious. This is the microheater. And so the thermal mass difference between these two is 5,000. The thermal mass of the aluminum oxide substrate on the left is 5,000 times that on the right. And so this greatly enhanced the sensitivity, reduced the response time to on the order of a few seconds, and it also lowered the power requirements substantially for this sensor application. This is an actual IR video of the microheater, the YSZ microheater being heated up and then turning it off, and you can watch how quickly the heat energy dissipates when we do this. So this is on the heating up of the very thin YSC microheater, and you can see the center area is locally heated. There's catalyst on top, so it's very specific to a very precise temperature where the catalyst is going to interact with the analyte. And then when you turn it off, you can see it's less than a second, or in the order of a second, for the thermal energy to totally dissipate when you turn this off. So we envision a duty cycle where this would be on for a certain time, sniff the area for the threat, and then shut it off, and do this periodically to save energy, but also to get back to baseline as well. So the way we did this is we started with 40 micron thick YSC substrates, and then energy was able to supply us with thinner and thinner substrates all the way down to 8 microns. So now at 8 microns, the thickness of the microheater thin film is on the same order of magnitude as the substrate, and you can actually see stresses due to the deposition of the thin film on the YSC substrate, which we addressed, but that's how thin, and this weighs on the order of micrograms. Okay, so these weigh hardly anything. And so imagine that the dimensions here are about 8 millimeters in this dimension and about 15 millimeters in that dimension. And the thickness is 8 microns of YSC and about half a micron of microheater and about a half a micron of catalyst on top of that. And so the reduction in thermal mass without sacrificing catalyst surface area. That's why the MEMS approach did not work very well, because the surface area of the catalyst was compromised. When you make the footprint that small, you don't have the same catalyst surface area. And so this is a way to achieve that. So this shows the effect of reducing the substrate thickness and its thermal mass on several things. The green here shows the very rapid response time, the slope of this line, with 8 micron thick YSC versus 12 micron versus 20 micron versus 40 micron. And I can't even show you the sensitivity under the same conditions for the 1 millimeter thick alumina substrate is down here in the mud somewhere. It doesn't even register. So these were all done at 175 degrees centigrade, and you can see these are the different powers that were required to get the sensor to that temperature to react with the analyte, that is, to get the catalyst to react with the analyte. This was done with tin oxide as a catalyst, and so you can see that that improvement in the sense that the response has been tremendously increased, the response time has been tremendously decreased, and the power requirement to power the sensors has been dramatically decreased, all to help with this idea of making the whole sensor package more compact. We also did something interesting as well. One of my PhD students in the ALERT program a couple of years ago, we published a paper where we tried to take a general catalyst like palladium and combine that with the specific catalyst, in this case it would be tin oxide, and look for the response to TATP with these nanoparticles dispersed in a matrix. And so with palladium nanoparticles dispersed in a tin oxide matrix, you could see this red response here at about 12 weight% of palladium. We got this bump, and that's because of the catalytic effect, the general catalytic effect of palladium in combination with the specific catalytic effect with tin oxide. And so this led to an interesting idea. We made palladium microheaters, and we intentionally made porous catalyst on top of this. And so that gave us even more of a bump in terms of response. And that's what the next slide shows, that this is a palladium microheater with a porous tin oxide catalyst on top. And this is a copper microheater. And you can see under the same operating temperatures that the power requirement for the palladium was a little higher, but you get so much more response, it's worth it. The reason why the power requirement for palladium is a little higher is that the inherent electrical resistivity of palladium is a little higher than that of copper. And so this is showing that difference really related to electrical resistivity, but you get this catalytic bump from the palladium. And so now we're using palladium microheaters to get maximum sensitivity, minimum response times, and low power requirements all in the same package. So, so this this shows sort of a summary, if you will, of our approach to make, first of all, thinner and thinner thermal mass sensors, switching over to a palladium-based microheater instead of a copper-based microheater, and how the power requirements would go down as we reduce the thermal mass, how the sensitivity would go up as we reduce the thermal mass, how the response time would go down as we reduce the thermal mass, and what kind of energies to power these microheaters as you reduce the thermal mass, all played into making the truly portable electronic trace detection system a reality. So what this shows is that the minimum power requirement was achieved with a copper-based microheater because of its lower resistivity. The maximum catalytic response and minimum response time was achieved with a palladium-based microheater, 8-micron YSE substrate, and also the minimum energy requirement was for a palladium-based microheater on very thin YSE. So these are thinner than actual paper. If you can imagine paper microheaters, these paper is much thicker than these ultra-thin YSE substrates. So that's the sensor side of things. And so if Brian could now talk a little bit about the integration of all this into BIPASS, which is this integrated sensor with a very thin battery for power supply, as well as flexible electronics and so forth to make the total package for this drone application. So Brian, if you want to take over, I'll advance the slide if you want, but.
Great, thank you, Otto. We at ITN have been working for several years on developing a unique solid-state battery platform. Given the nature of how much time we have today, I won't go so much into that, but we will be giving a webinar sponsored by the FlexTech Alliance on that technology on the 29th of July, and anybody can reach out to me if they would like to learn more about that. But basically what we've been doing is similar to what they've done at the University of Rhode Island and Otto's group, is to put the battery onto a very thin YSE substrate from energy, and therefore most of the volume is taken up by active battery materials instead of packaging. This is a vapor deposited solid state material done same way semiconductors are made. It's just using battery materials instead of silicon. And so we can deposit the batteries onto the YSE substrate, stack them together in parallel to get capacity. And what we've learned is now is similar to the URI group, is that we can make paper thin batteries, and you start to put that into these flexible electronic systems, and the electronics themselves start to be very thick relative to the battery. And so we had the good fortune of starting to work with many partners, as Otto indicated in the bottom of the slide. You see several of them, of how we could start to envision having an entire sensor system that could get into this truly paper thin format. And it takes advantage a lot of some work that was done at American Semiconductor, where they have processes to take high performance silicon out of a packaged die format and bring it into a bare die and a polished thin bare die, where high performance silicon can be 30 microns thick and still integrated into a fully functional printed circuit. And so then that allowed us to start dreaming of this bypass concept, where the bottom layers would be the battery and the power supply, and then the top layers would be printed circuits and or sensors, as those that are developed at the University of Rhode Island. And therefore you could envision the entire vertical stack could be less than a sheet of paper thick and integrate all this functionality. Another way to think about it is basically we can offer a self-powered circuit board where we give this battery to folks and they can print their explosive sensors or high-performance silicon electronics right on top of the battery. And we've shown a lot of those functions can be accomplished. Otto, why don't you go to the next slide? And so the focus of the effort so far in the project has been both to integrate the charge control electronics from the battery side, to protect it's a lithium-based battery, so it has over voltage and under voltage protection and all the things that you're used to with a lithium-ion battery technology, so it can use commercial technology, but also how to integrate it with the sensor. And so you see in the bottom left-hand corner, ultimately, how small one of these units can be. That's an actual solid-state battery with one of the University of Rhode Island sensors mounted directly onto the battery, and that's less than a couple hundred microns total thickness there. Now that image just represents the sensor and the battery without all of the signal processing electronics that are required. At this stage of the project, the signal processing and all of the circuitry is done in a breadboard fashion, as you see in the image in the upper right-hand corner. But we were able to integrate the ETD sensor directly on top of the battery and place it into the analyte chamber and operate it as kind of an integrated device as the first step towards this bypass. And one of the things that really drives this is the need to get the battery, the power of the system much smaller. And Otto showed you a lot of how they've been successful at improving the sensor as well as the signal electronics to get that power down. And the first demonstration we did then was we were able to detect acetone basically at room temperature at parts per million level with this sort of an architecture. And it's very, very promising. So Otto, why don't you go to the next slide? And, without going into a ton of detail, the other thing that we were able to learn in this project so far is that if you look at the function for the signal processing and the telemetry and all the things you need for a complete sensor system, not just the sensor itself and the power supply, but all of the supporting electronics, is they're all available in these kind of microcontroller units that could be put through the American semiconductor process and get into the thin die format and put into a printed circuit. And so if we start to learn of all the functions that need to be integrated into that, the digital analog conversion, the analog digital conversion, some of the wireless communication and all the rest of that stuff, we've identified a series of commercial off-the-shelf parts, some of them already available from American Semiconductor in the thin die format. And we showed that we could actually fit the entire footprint of a full sensor system right onto the surface of the battery. And so, the next steps of the evolution of this really are compatible with the bypass. And as Otto indicated, I mean, it can go anywhere from the explosive trace detection to narcotics to healthcare to all kinds of things. And so you really have this ability to have a label that has an entire sensor system built into it. And it can be very exciting, but it's only possible because the sensor technology and the battery technology and the electronics all can be in this very, very thin format, taking advantage of the benefits of these thin and flexible ceramic substrates. So, Otto, I think the next slide is the conclusion, which is probably timely.
Do we have time for the conclusion, Emil, or are we?
Yes, you have 3 more minutes left.
Okay. So we were able to demonstrate thin film sensors on these ultra thin YSE substrates that were part of our overall efforts to reduce the thermal mass of what we had before to these really ultra thin substrates, reduction in mass by more than 5,000 times. And these YSE based sensors exhibited highly localized heating and cooling due to thickness anisotropy as well as the material anisotropy of the YSE. And this resulted in very reduced response times, much greater sensitivities and response magnitudes, and overall lowering the energy or power requirements. So these improvements were achieved at reduced operating temperatures, which before all this thermal mass reduction, we had to operate the sensors anywhere from 300 to 500 degrees C. We now were able to lower the operating temperatures, which also lowers the power requirements. And so this really enabled us to do real-time sensing in the future with a drone or a wearable platform. In other words, we now think a wearable or drone platform using this technology that Brian discussed briefly and that I tried to demonstrate is now a real possibility. The electronic trace detection system, which is ours, was successfully integrated into a bypass architecture, and that means all the components, that is the sensors, signal processing, electronics, etc., literally in an ultra-thin package, which weighs almost nothing. Remember that I mentioned that some payloads on drones are as small as 2 grams, so that really restricts what you can do. But imagine the possibilities with such a package on a drone to fly in, assess threats, and then fly out. So that's all I have today. Emma, I think I turn it over to you, or you can.
Yeah, thank you, Otto and Brian. We did have a couple of questions from the audience. One of the first questions is, to what temperatures can the YSZ heater reach?
We have taken it to 900 degrees C. YSC, if you're a material scientist, is widely used for high temperature solid oxide electrolyte fuel cells that operate for thousands of hours at temperatures of 800-900 degrees C. So temperature cycling is not a problem for this material. We have taken it in this thin form to 900 degrees C to do some annealing of our films at times. So it's a very stable substrate material, even in this thin film. By the way, this is so flexible, you can curl it up upon itself. I don't know if one of those slides showed, you can essentially roll up this as a sheet into a coil, if you will.
Second question is, how are you defining response time?
So the response time is really that the slope. So we introduced it takes a while for the analyte to get to the sensor. So we're not we can put the analyte as close to the entrance of where our sensors are located. That plumbing will reduce the response time. So we can reduce that to the order of a few seconds. But you can see the slope of the I don't know if I don't have the screen still. You can see the response time is that slope, if you will. Once the analyte gets to the sensor, you can see it's very, very fast responding and can be done well within 5 seconds or so. And we have been testing this whole system in a CT tunnel environment to see if we couldn't scan the area or headspace around luggage in a CT tunnel at the same time the luggage is being x-rayed. And so we think our response times are fast enough that we can capture that information the same time that a package or a piece of luggage would be scanned using x-rays.
The next question is, what sort of selectivity have you observed when co-delivering like molecules, for example, acetone with TATP, DNT with TNT, etc.?
I'll back up for a second. So in addition to having the orthogonality from the conductometric sensor, which is just measuring the change in electrical conductivity of the oxide catalyst as it's exposed to the analyte. So there's one catalyst and it's being interrogated by 2 different ways. One is this thermodynamic approach, which I talked about today, and the conductometric approach has been around for a while for metal oxide sensors, where you measure directly the electrical resistivity or conductivity as it's exposed to the analyte. So we have that sort of orthogonality. But in addition to that, the thermodynamic sensor has a sign. That is, it can be exothermic or endothermic, depending on the analyte and the catalyst. And so we have that, sometimes we see a negative response, okay, depending on the analyte. And so we can sort of separate out acetone from TATP, even though acetone is a decomposition product of TATP, we can still separate out those effects from the sign change, okay, and the other orthogonalities that are built in. But we do have, the other issue is for improving sensitivity is we're now doing arrays of sensors. So we have, I have so much data to present if you wanted to, but imagine that a copper oxide sensor or a tin oxide sensor has a different thermodynamic sign response for a given analyte. One would be exothermic, one would be endothermic. And as a result of that, we have this unique selectivity because, and the other thing is that sometimes catalysts don't respond at all. So we've done things where we take 5 or 6 catalysts and, for example, indium oxide, if you use that as a catalyst, it doesn't respond to TATP, whereas other catalysts like tin oxide and copper oxide do respond to TATP. So and indium oxide responds to acetone, for example. So we can mix and match catalyst with analyte, and we have these very specific outcomes that we can put together in a sensor array. So I don't know if I'm clear on that, but.
Okay. We just have 2 more questions. I'll go through them really quickly. How does the analyte get into the sensor system for drone applications?
So that's a great question. And I don't know if we have a slide. I can't remember, Brian, but we did build up this layer like Brian was talking about. And so you can imagine that these layers would be on the wing of a drone. And so you would fly your drone to an area and you would slow the velocity down so that you reduce the flow velocity. You would just allow the sort of convection airflow over the wing to get to the sensors. So the sensors would be mounted on the wings. So with all the associated electronics and battery power supply, et cetera. So we wouldn't do anything special. We would have everything just located on the wing. It would be conformal to the wing surface, and that's the way we were envisioning it. We wouldn't need tubes or anything like that because of sort of the forced convection from the drone flying. We'd have to determine what those velocities would be, but drones can hover. They can do all kinds of things that would be helpful in quantifying what kind of flow rates we need to actually sense.
Okay, and the last question is, what is the cost to create a drone-based system, and can the system respond to an unknown threat versus a pre-programmed threat?
So that's why we're doing, I'll answer the last one first, and Brian can jump in too. I think that the array approach is the way to identify, as long as we had a library of sort of responses for the array to call up, I think we could identify the threats. Okay, I don't know about an unknown threat. We would have to have a library of threats to do this. And so in terms of cost, I'm not sure. I think, our end of things, that is the sensor end of things, would certainly, these are amenable to mass production using thin film technology and sort of a lot of the techniques that are used to make integrated circuits. So I don't imagine them being the cost driver. That is our sensors, because you could manufacture those in large quantities. But the other components, I'm not sure of what the final cost would be when you put that all together. Maybe Brian has some idea on final cost for a drone, but I don't think it would be driven by the actual sensors.
Yeah, we haven't done a cost analysis on the whole sensor system yet. I can tell you that the battery itself in volume production would be on the order of dollars per battery, and I believe that, as Otto suggests, that the sensor itself would be even cheaper because it is so small, and you much like the semiconductor analogy, you can make many of them in a wafer, so to speak. In volume, that it could be cheap. So I think it can be a cost-effective system. I don't have a quantitative number though, because I haven't done the analysis of the cost of the thin die and printed circuit integration. Other folks are the experts on the team in those areas of the technology.
Great. Thank you, Otto and Brian, for the wonderful presentation. And thank you, everyone, for joining us today. We will be sending out an email later today with the survey, so be on a lookout for that. And as a reminder, we do have an upcoming webinar on July 22nd with Professor Eric Miller of Tufts University and Dr. Roman Blanchard of Pendar Technologies. So thank you again, and enjoy the rest of your day.
Thank you.
Take care, everyone.
Thanks, everyone.